Hello, I am Indranath Sengupta from IIT Gandhinagar. Let us start our course in linear algebra. The first chapter is on systems of linear equations, and the first module is divided into three sections broadly: system of linear equations, homogeneous and non-homogeneous system of linear equations, and elementary row operations and elementary matrices. Later on, we will get into the abstract definition of vector spaces, and then systems of linear equations etc. will be revisited through linear transformations. Let us start. Let us start with a field f. So, right now we are not really trying to define an abstract field, which will come later on. So, for the time being, you can think the field f denotes either the set of rationals or reals or complex numbers, or z mod p, where p is a prime number, which is of course a finite field, and the other three examples that you see are infinite fields. Now, a system of equations, to be precise a system of m linear equations in n unknowns over a field f, is given by what you see within braces and with the symbol E. So, you can see that there are m of them, m linear equations, and these aij's which you see, which are elements of the field f. So, in particular, if you think your field is either rationals or reals or complex numbers or zp, then they are members of that field f, and so are the bi's which are appearing on the right hand side of the equality sign. So, we also call them simultaneous linear equations, which is also a very standard or popular name. So, let us call them system of linear equations, and m and n of course are positive integers, as you can see. So, and I and j are running indices. I is running from 1 to m and j is running from 1 to n. Now, this is quite a convenient notation in terms of matrices, that system of equations E is often written as Ax is equal to B, where A is in matrix notation this m cross n matrix. You can see what they are nothing but this the so called coefficients of those equations, the aij's, which are elements from F. So is B. So, B is a column matrix, and X, which you see, is precisely what we call the matrix of indeterminates or variables. So, x1, x2, xn are the so called unknowns or indeterminates, and this matrix, another chap is this A vertical line B, usually that is how we write it, which is nothing but the matrix A, and then there is an extra column on the right hand side, which is nothing but that B1, B2, Bm, and this is what we call the augmented matrix. And this augmented matrix is the one which we usually work with when we try to solve the equations. We test solvability of the equations, look for number of solutions, and various other questions like this. Okay. So, now let us define what is called a solution of this system. F to the power n, you know what it is. So, F is the field, F to the power n is the Cartesian product of F n times, and the elements of F to the power n are all n tuples. So, let us use this vertical notation for denoting a typical element in F to the power n. It is also written with the horizontal notation, but let us use the vertical one because it is convenient. So, a solution of the system E is an n tuple alpha 1 to alpha n in F to the power n, such that A dot alpha 1 to alpha n is equal to B. So, that means if we substitute x1 equal to alpha 1 and so on xn equal to alpha n in the system E, then they satisfy the equations simultaneously. So, let us now get into some simple examples. To begin with, x1 minus x2 equal to 0, x2 minus x3 equal to 0. So, you can see that there are two equations. So, m is 2, but there are 3 unknowns, namely x1, x2 and x3. So, n is 3. So, the matrix A, which is the so called coefficient matrix, would be 1, minus 1, 0 in the first row, 0, 1, minus 1 in the second row. X, which is the matrix of indeterminates or unknowns, is x1, x2, x3, which is a 3 cross 1 matrix, and B is 0, 0. So, in matrix notation, Ax equal to B does make sense, because A is a 2 cross 3 matrix and X is a 3 cross 1 matrix. So, the matrix multiplication is indeed meaningful and giving rise to a 2 cross 1 matrix, which is your B. Now, a typical solution, of course, here there are 3 unknowns. So, a typical solution would belong to f to the power 3. So, a typical solution would look like alpha 1, alpha 2, alpha 3. But if you look at the equations carefully, then you can see that x1 must be equal to x2 and x2 must be equal to x3. So, a typical solution would be of the form alpha, alpha, alpha. So, all the 3 spots are filled in with one particular real number or an element of the field f, and this alpha, alpha, alpha can be rewritten as alpha and then 1, 1, 1. So, this is what we call a scalar multiple of the vector 1, 1, 1. We will come to it, come to a more precise definition later. Another example. So, you can see there is only one equation. So, m is 1, 3 unknowns, n is 3. So, the coefficient matrix is given by A, which is a row matrix in this case, 1, minus 1, 1, x, which is the matrix of indeterminates, which is a 3 cross 1 matrix, because there are 3 unknowns. B, the matrix is just a 1 cross 1 matrix, because there is only one equation and there is only one B1, namely 1. So, a typical solution again would lie in f to the power 3, and if you solve it, it is very easy to see that if you allow x1 and x2 to vary freely, call them alpha beta, then your x3 is automatically determined and it is 1 minus alpha plus beta. So, a typical solution is of this form. Now, what is noteworthy here is that if your field f is an infinite field, for example, Q, R or C, then you have infinitely many choices for alpha and beta, and therefore, there are infinitely many solutions possible. Now, keep this very form alpha beta 1 minus alpha plus beta in mind, and then you see that. So, if you look at a solution, a typical solution is of the form alpha beta 1 minus alpha plus beta. We can rewrite it as alpha 1 0 minus 1 plus beta 0 1 1 plus 0 0 1. Now, what is interesting here is that these two 1 0 minus 1 and 0 1 1 are solutions of the corresponding homogeneous equation, that is x1 minus x2 plus x3 equal to 0. We have not defined homogeneous equation yet, but that is precisely what we would be calling the corresponding homogeneous equation, that is when there is 0 on the right hand side of the equality sign, and 0 0 1 happens to be a particular solution of the equation x1 minus x2 plus x3 equal to 1. One more example, 2 equations, 2 unknowns. So, A is a 2 cross 2 matrix given by the coefficient. So, 1 minus 1, 2 minus 2, and then X is the matrix of indeterminates or unknowns, B is 0 1. Now, there is no solution to this system for the reason that if you look at the first equation, then x1 minus x2 is 0. And if you look at the second equation, then x1 minus x2 is half, and these two cannot happen simultaneously. So, therefore, there is no solution possible for this particular system of equations. We only make a modest assumption, which is also important though, that the field f in this case is either Q or R or C, and it is not a ZP, because otherwise there could be, to be precise, a problem with defining half. Let us now formally define what are called homogeneous and non-homogeneous systems of linear equations. So, the system of equations in matrix notation, you have already seen that it is written as Ax equal to b. It is said to be homogeneous if the matrix B on the right hand side is the 0 matrix, otherwise it is called a non-homogeneous equation. What is interesting is that every homogeneous system of equations Ax equal to 0 has at least one solution, namely the trivial solution. That means all the spots are filled in with zeros. That is very easy to see, because if you just substitute x1 equal to x2 equal to x3 and so on, xn equal to 0 in the system of equations E, then all the equations are satisfied simultaneously. And a non-zero solution is called a non-trivial solution to the system. So, by a non-zero solution we mean that there is at least one entry which is not 0. So, let us now see the first theorem. Every homogeneous system of linear equations over an infinite field has infinitely many solutions if it has at least one non-trivial solution. This is easy to see. So, let us start with a non-trivial solution alpha of a homogeneous system of equations. If alpha is a non-trivial solution, that means there is at least one alpha I which is not 0. Now, if we choose any lambda from f star, what is f star? F star is precisely the set of all non-zero elements in the field. Then lambda alpha is also going to be a solution and a non-trivial solution. It is definitely non-trivial because let us say alpha I is not 0, then lambda alpha I is also not 0, and solution to the homogeneous system, which is also easy to see, because if you just substitute x1 equal to lambda alpha 1 and so on xn equal to lambda alpha n, then the equation E is satisfied. Examples. So, the first example, of course, it is a system of homogeneous equations because of the zeros on the right hand side of the equality sign, and it is not difficult to see that the only solution possible is the trivial solution. Whereas, in the second example, which is also homogeneous, there are infinitely many solutions if the base field is an infinite field. That is also not difficult to see, because x1 plus x2 is equal to 0 implies that x2 is equal to minus x1, and therefore, if the field is infinite, then we have infinitely many choices for x1 and therefore x2. Now, let us introduce this theorem, which we have already seen before in some sense. When we discussed examples, we saw that solutions can be written in terms of solutions of corresponding homogeneous equation and a particular solution. So, this theorem talks about the same. Let Ax equal to be a non-homogeneous system of linear equations with a solution alpha. So, alpha is a particular solution. Now, every solution of Ax equal to b is of the form alpha plus u, where u is a solution of the homogeneous system of equations Ax equal to 0. Proving this is simple. Alpha is a solution of the system, therefore, A alpha is equal to b. If u is a system of the corresponding homogeneous system of equations, then Au is 0. Then A dot alpha plus u, this dot means the matrix multiplication, is equal to A alpha plus Au. Now, A alpha is b and Au is 0, therefore, you get b on the right hand side. This shows that alpha plus u is a solution of the given system of equations. Conversely, if you start with a solution to the system of equations Ax equal to b and call it V, then you can write V as V minus alpha plus alpha, and it is easy to see that A dot V minus alpha is A V minus A alpha, but A V is B, A alpha is B, and therefore you get a 0, which shows that V minus alpha, if you call it U, then it is a solution of the corresponding homogeneous system of equations A x equal to 0. So, this proves the theorem. Examples once again. So, you see a non-homogeneous system out there. If you eliminate x1, you get x2 equal to 5, therefore, x1 will be minus 11 if you substitute back x2 in your equation, and then alpha is minus 11 comma 5 is a particular solution of Ax equal to b. Now, the corresponding homogeneous system of equations is given by x1 plus 3x2 equal to 0 and 2x1 minus 5x2 equal to 0, and this has only the trivial solution, which is also very simple to check. Therefore, the only solution possible to this system of equations would be minus 11 comma 5. Next example, once again 0 1, call it alpha, is a particular solution of the system of equations, and a typical solution of the corresponding homogeneous system, which is x1 plus x2 equal to 0, would be u comma minus u. Therefore, by the previous theorem, a typical solution of the given system of equations would be of the form 0 1 plus a typical solution of the corresponding homogeneous system, that is u comma minus u, and therefore, it is of the form u comma 1 minus u, which is of course easy to see from the equation itself. So far, we have introduced some basic definitions about systems of linear equations. We know what is called a homogeneous system of linear equation, what is a non-homogeneous system of linear equation, what is meant by a solution of a system of equations. We have also seen a couple of theorems, basic ones. Now, we are going to discuss how to solve a system of equations. We will introduce the concept of elementary row operations, and we will learn the corresponding matrix analog in terms of elementary matrices. And our aim is to talk about the celebrated Gaussian elimination, which gives a very precise algorithm for solving a linear system of equations. Let us start with elementary row operations. Let us start with an m cross n matrix over a field F. Let the matrix be denoted by A. Let us first introduce what are called elementary row operations on a matrix. So, there are three kinds. The first one, which is denoted by R suffix ij, which stands for interchanging the ith row and the jth row of the matrix A. The second kind, alpha Ri, which means that multiplying the ith row of A by a non-zero scalar alpha in F, that means a non-zero element of the field F, which is alpha. And the third one, which we write as Rj tilde is equal to Rj plus alpha Ri, which means that adding alpha times the ith row of the matrix to the jth row of the matrix, nothing happens to the ith row, but the jth row changes, and the new jth row is denoted by Rj tilde. So, these are what are called the elementary row operations. Now, we start with a matrix A, and if we keep on applying these elementary row operations in some sequence, and if we achieve finally the matrix B, then usually it is denoted by this symbol A tilde B through rho, where rho is an elementary row operation of one of these three kinds. An n cross n elementary matrix E is defined as the matrix which we obtain if we perform an elementary row operation on the n cross n identity matrix I n. We saw three kinds of elementary row operations, and therefore there are three kinds of elementary matrices as well. Let us look at them. If we consider n is equal to 3, then what you see on your left is the n cross n, which is 3 cross 3 identity matrix. We apply R12, that is row operation of first kind. That means we are just flipping the first two rows, and then the outcome is what you see on the right hand side. That is elementary matrix of first kind. Then the type 2, that means elementary row operation of the second kind being applied to the 3 cross 3 identity matrix, which you can see is the first row is being multiplied by a non-zero element A from F, giving rise to A00, 010, 001. This is an elementary matrix of the second kind. And type 3, the application of elementary row operation of the third kind gives rise to what you see on the right hand side. What we are doing in this case is we are multiplying A times the third row to the first row for some A in F, and the outcome is 10A, 010, 001, which is an elementary matrix of the third kind. If E is an elementary matrix obtained by performing an elementary row operation on In, then EA is the matrix obtained by performing the same elementary row operation on A. This is a very important observation. In other words, an elementary row operation on a matrix A is the same as pre-multiplication or left multiplication of the matrix A by the suitable elementary matrix E. So, an elementary row operation can also be seen as a matrix multiplication on the matrix A. Let us look at this example. The matrix A is the one you see, that is 010, 100, 001. If we apply the elementary row operation of the third kind first, which is adding the first row to the second row. So, what is changing here is the second row, and nothing happens to the first row. As you can see, the second row has become 110 now. The first and the third rows are unchanged, giving rise to what we call A tilde. Now, suppose I do the same on the 3 cross 3 identity matrix I, and then what we get is 100, 110, 001, which is surely an elementary matrix of third kind. If we see EA, that is left multiplication of A by the elementary matrix E, then what you see is that the outcome is 010, 110, 001, which is nothing but your A tilde. So, this is a quick illustration of our previous comment that an elementary row operation on a matrix A is the same as a left multiplication by a suitable elementary matrix. Now, this is a very important observation about elementary matrices. It says that elementary matrices are invertible, and the inverse is an elementary matrix of the same type. How we prove this is the following. Suppose E is an n cross n elementary matrix obtained by an elementary row operation row on In. Now, if we reverse the steps of row, then we get back In. And what is interesting here is that this reverse operation of row is also an elementary row operation of the same kind. Therefore, we can say that there is an elementary matrix E tilde such that E tilde E is I. This is because the reverse row operation on E gives back I, but this proves that E is invertible and inverse is nothing but another elementary matrix. We can define elementary column operations similarly. An elementary column operation on a matrix A is the same as post multiplication, that is right multiplication of A by the suitable elementary matrix. We have come to the end of module 1, and a very important thing that you have learnt in module 1 is elementary row operations and elementary matrices. We will now see in module 2 how to use them for solvability of a system of linear equations, and as I mentioned, we will be talking about the Gaussian elimination.